Have you noticed, when you look at a feather, there's a bunch of little fibers that come out of the central shaft. And they're all linked together. When I take this feather and I pull it, all those fibers are stuck together. And I can pull them apart, but I have to work at it. I have to tease them apart. It turns out there's little barbs on the edge of each one of those fibers that holds them all together and gives the feather its structure. We can use a laser to help us see the structure of those barbs. Let's take a look. If I take the laser and I shine it through the feather, I'm going to get a pattern on the screen. And if I hold the feather just right, and I look at the pattern on the screen, I can see that there's a pattern of light and dark. What I'm actually seeing is diffraction pattern. The light goes through and it shines on a bunch of the different barbs at one time. And so it can go through certain places and it's blocked other places. And so I have light coming from multiple places on the feather. I have constructive and destructive interference on the screen, and I get a diffraction pattern. And analyzing the structure of the diffraction pattern allows me to say something about the structure of the feather. We're going to look at a simpler problem today, but one that works exactly the same way. I've got a diffraction grating, and this has a network of very closely spaced lines on here, so close you can't see them. But if I take this grating and I put it in front of the laser, I get a series of spots on the screen. And the spots are a diffraction pattern from constructive and destructive interference. Now let's take a look. I take this diffraction grating and I put it about 5 centimeters from the screen. I get a network of dots on the screen. I get a network of dots on the screen. And if I measure the width of the pattern that I get, see the width of the pattern that I get is about 13 centimeters. So slide 5 centimeters from the screen. The width of the pattern that I see, I'm seeing 2 dots on either side, a total network of 5 dots. And the width from here to here, 13 centimeters. That's enough information to set up and solve a problem having to do with this very diffraction grating. Let's take a look. Here's our problem today. Light from a green laser pointer, wavelength 530 nanometers, shines on a diffraction grating and makes a pattern of bright spots on a screen 5 centimeters behind the grating. There are 5 bright dots on the screen. The distance between the 2 outermost dots is 13 centimeters. What is the spacing of the grating in lines per millimeter? Let's draw a picture of what the situation looks like. So we have a diffraction grating, and there's a screen that sits behind it at some distance. A laser comes in, and some of the light from the laser goes straight through and hits the screen and makes a bright spot on the screen. We also saw there were bright dots which were out to the side. Those are our orders of diffraction, and we saw a total of 5 dots on the screen. There was a total of 5 bright spots. That's what a situation looked like. And let's think about the numbers that we measured. We measured the distance between the diffraction grating and the screen. We measured that to be 5 centimeters. And we measured the width of the pattern from one side to the other to be 13 centimeters. That's our physical situation. Now we're going to draw a top view of this picture, and we'll look at it in a way that you're more accustomed to seeing. Okay, we've got our diffraction grating right here. Laser comes in, shines through the diffraction grating. Some of the light continues through, hits the screen, makes a bright dot. That's my m equals 0 fringe. But I also had first order, m equals 1, and second order, m equals 2, and I get that on both sides. And we found that the distance from the diffraction grating to the screen, 5 centimeters, the width of the pattern from the bright dot on the left to the bright dot on the right, 13 centimeters. Those are our 2 numbers that we need. Let's take a look at our basic relationship for diffraction. It's this: d times the sine of theta m is equal to m times lambda. Now, let's remember what everything in this relationship corresponds to. D is the spacing of the diffraction grating. Theta m is the angle that the light comes out of the diffraction grating. And lambda is the wavelength of the laser, so that's the wavelength of the light. Before we can use this relationship, we have to say some things about how it corresponds to the pattern that we see. First off is this. The equation is just given for one order. There's one value of m, okay? And we were given the width of the whole pattern. So we need to take this and we need to tease it out and pick out one particular order. And since we're given the width of the pattern between the second order fringe on one side and the second order fringe on the other side, it makes sense to talk about it in terms of the second order. So let's redraw the picture, and let's do just the second order fringe on one side. Now our picture is going to look like this. Here's our diffraction grating. Light comes in. Some of it goes straight forward. Some of it diffracts, makes a second order fringe on the screen. And so we have these two dots. Now we're interested in the angle. We're interested in this angle, theta, right here. That's going to be theta 2. That's the angle for the second order fringe. And how are we going to calculate that? Well, we can use some trigonometry to say something about that, because we know the distance from the diffraction grating to the screen. We also know this distance right here, the distance to the side at which the dot for the second order diffraction maximum appears. Well, actually we don't know it, but given the information we have in hand, we can compute it. Remember, the width of the whole pattern was 13 centimeters. Given that, what's this distance right here? The distance at which the second order maximum appears from the center of the pattern. We'll give you some choices. Well, that distance is just half the total width of the pattern. So that distance right here, 6.5 centimeters. The distance of the diffraction grating from the screen, 5.0 centimeters. So we can say something about theta 2. Specifically, we can say this. The tangent of theta 2, the tangent of the angle for the second order diffraction maximum, is just equal to 6.5, the opposite side of the triangle, divided by the adjacent side of the triangle, 5.0. If we use that to calculate an angle, here's what we get. We get theta 2 is equal to 52 degrees. I'm going to pause and do a quick assessment as we go. That seems about right in terms of what I observed as I was setting that up. So far so good. Let's revisit our basic relationship. It's this. D sine theta m is equal to m times lambda. Now we're looking for d, so we'll rewrite it to solve in terms of d. D is equal to m times lambda divided by the sine of theta m. But remember, we're looking at a situation where m is equal to 2. Theta 2, theta for that particular order, is equal to 52 degrees. And lambda, we know lambda, that's 530 nanometers. But we need to put that in our usual SI units. So that's 530 times 10 to the minus 9th meters. So we have a relationship, and we have everything we need in order to solve that relationship. Let's do that. Okay, so the spacing of the grating is this. D is equal to m, which is 2, times lambda, which is 530, times 10 to the minus 9th meters, divided by the sine of the angle for the second order maximum, which is 52 degrees. If we put in numbers and calculate a value for D, here's what we get. We get 1.33 times 10 to the minus 6th meters. But we were asked to calculate what the grating spacing was in lines per millimeter. So first off, let's put that meters in millimeters. Well, if I multiply by 1,000, I can convert meters to millimeters. So it's 1.33 times 10 to the minus 3rd millimeters. But we weren't asked for the grating spacing. We were asked for the number of lines per millimeter. And how do I turn this number for the grating spacing into lines per millimeter? What is the lines per millimeter for this particular spacing? We'll give you some choices. Well, if we know that each line has a width of 1.33 times 10 to the minus 3rd millimeters, the number of lines per millimeter is just 1 divided by this number right here. So it's 1 divided by 1.33 times 10 to the minus 3rd. And if we do that, that gives us a spacing of 750 lines per millimeter. Next step, it's how we always finish every problem, is to look at this number and see if it makes sense. And we certainly expect this one to, because it was based on physical measurements that you saw being made. Let's take a look. So the laser shines through the grating, makes a pattern of dots on the screen, and we've got two diffraction orders that show on each side of the grating. So I'm going from m equals 2 on this side to m equals 2 on that side. We measured this distance, we measured this distance. It allowed us to calculate the spacing of the grating. We got 750 lines per millimeter. And it turns out this one's got a little label on it that tells me, and it says 750 lines per millimeter. That's a typical number for a diffraction grating that's going to spread the light out pretty widely. So our answer works. Again, not a surprise. Physics is about the world around us. You saw me make the measurement. We use the numbers from the measurement to compute the calculation, and it works, as we'd expect.